Somewhere on a mountain in Chile, a telescope the size of a small building just took a picture that no human telescope has ever taken before. Stay with this story until the very end, because the last part of it is the piece almost nobody online is talking about yet, and it changes the way you will look at the night sky from now on. Let's start with the basics, because understanding what this machine actually is comes before understanding why the entire world of astronomy is talking about it. This is the Vera C. Rubin Observatory. It sits on top of a mountain called Cerro Pachon, high in the Chilean Andes, in one of the driest and darkest places on the planet. Astronomers chose this exact spot on purpose. No clouds, no city lights, no moisture hanging in the air to blur out the stars. It is quite literally one of the best possible places on Earth to look up into deep space. But this observatory is not just another telescope sitting on a hill. Its main mirror is 8.5 meters wide, almost as wide as a tennis court is long. Attached to that giant mirror is a camera, and not a normal camera, not even a professional camera. This is the largest digital camera ever built by human beings. It carries 3,200 megapixels. A typical smartphone camera holds somewhere between 12 and 50 megapixels. The single camera carries 3,200. Every photo this telescope takes is so massive, so detailed, that displaying one full image at its true resolution would require roughly 400 separate 4K television screens lined up side by side just to show a single picture. And here's the part that really shows what this machine is capable of. This telescope does not take a slow, careful photo once in a while the way older observatories do. It moves fast. It captures a brand new, incredibly detailed image of the sky roughly every 40 seconds, then swings to the next patch of sky and does it again, all night, every night, taking about 1,000 images each night for 10 years straight without stopping. That 10-year commitment is not incidental. It is the entire point of the project. The mission behind this observatory, the one everything has been building toward for 2 decades, is called the Legacy Survey of Space and Time. Instead of taking a single snapshot of the universe, Rubin Observatory scans the entire southern night sky in ultraviolet, visible and near-infrared light, revisiting the same regions roughly every 3 days, continuously for an entire decade. Stitch those images together, and you don't just get a picture of the universe, you get a movie. A real, observational movie of the night sky changing over time, made from actual measurements, not animation, not simulation. Scientists working on this project have called it the greatest cosmic movie ever attempted. On June 30th, 2026, that movie officially started rolling. But before getting to what has happened since then, it's worth rewinding, because this observatory carries a very human story behind its name that most coverage skips entirely. It is named after Vera Rubin, an American astronomer who, decades ago, was studying how galaxies rotate. She noticed something strange. Galaxies were spinning in a way that should not have been possible if you only counted the visible matter inside them, the stars, the gas, the dust. We can actually see through a telescope. Based on visible mass alone, the outer edges of a galaxy should spin much slower than its inner regions, the same way planets far from the sun move slower than planets close to it. That is not what Rubin found. The outer stars in these galaxies were spinning almost as fast as the inner ones. Something invisible had to be out there, adding extra gravity, holding those galaxies together from the outside in. Her careful, patient work became some of the strongest evidence scientists have ever assembled for the existence of what we now call dark matter, a substance that gives off no light, that cannot be seen directly, yet appears to make up a large share of the mass in the universe. Vera Rubin spent her career being precise, careful, and completely devoted to simply watching the sky and trusting what the numbers told her. So when the National Science Foundation and the Department of Energy built the most advanced survey telescope in history, they named it after her. It fits, because this observatory exists, in many ways, to continue the exact work she began, chasing answers about dark matter and its strange partner, dark energy, the mysterious force that appears to be pushing the entire universe to expand faster with every passing year. Before moving forward, it helps to understand how this camera was actually built, because the engineering behind it is its own story. The camera at the heart of this observatory was constructed by the Department of Energy's SLAC National Accelerator Laboratory, working alongside teams from around the world. It is roughly the size of a small car and weighs around 3,000 kilograms, yet it has to operate with such precision that it can capture faint, distant light, without the smallest vibration throwing off the image. Inside it are 6 large optical filters, each designed to capture a different band of light, from ultraviolet through to near-infrared, allowing scientists to study everything from hot young stars to cool, faint, distant galaxies within a single coordinated survey. Every image the camera captures has to pass through layers of calibration, checking focus, exposure, and alignment before it becomes part of the official dataset. That's exactly why the commissioning phase took as long as it did. A mistake at this stage could ripple through 10 years of observations. The team behind the project has been open about this, explaining that the decision to officially begin the survey came only after a careful operational review covering image quality, survey speed, system uptime, reliability, and calibration accuracy. Because once the 10-year clock starts, there's no going back to quietly fix small errors after the fact. All of that raw data does not simply sit on a hard drive somewhere in Chile. It travels to a data facility in the United States, hosted at SLAC, where it becomes available to the wider scientific community. One of the major science teams working with this data is called the Dark Energy Science Collaboration, a group of researchers spread across the globe using Rubin's observations to make high-accuracy measurements of the universe's fundamental properties, the exact numbers describing how fast the universe is expanding and how matter is distributed across the cosmos. What makes this project genuinely different from almost anything before it is that this data will not be locked away behind closed doors. Scientists involved have said, this marks the first time this much astronomical data will be openly available to so many people at once, opening the door for researchers everywhere, not only at major institutions, to participate in real, cutting-edge discovery. Even members of the public will eventually be able to explore parts of the dataset themselves, getting hands-on access to a stream of information that used to belong only to professional astronomers working with the world's largest telescopes. Now let's walk through what actually happened, step by step, using the real dates and real numbers behind this story, on June 23rd, 2025, in Washington, D.C. The team behind Rubin Observatory held a public event called First Look, the moment the world saw real images captured by this telescope for the very first time. One of the earliest images released was a composite of two glowing nebulae, clouds of gas and dust in deep space known as the Trifid Nebula and the Lagoon Nebula. Other telescopes have photographed these clouds before, but never like this. That single image was built by combining 678 separate exposures, captured across roughly 7 hours of observing time. In total, that one image contained about 2 trillion pixels of data, 2 trillion, inside one glowing photograph of colorful cosmic clouds with enough detail to zoom in endlessly and keep finding stars hiding inside dust that older telescopes simply could not resolve. Another image released that same day showed a section of the Virgo cluster, an enormous collection of galaxies. In that single frame, countless galaxies appear scattered across the background, spiral shapes and elliptical shapes glowing quietly behind bright foreground stars from our own Milky Way. Scientists expect that over the full 10 years of this survey, Rubin Observatory will help catalog roughly 20 billion new galaxies. 20 billion galaxies currently sitting out there in the darkness with no record at all, waiting to be captured by this camera. But here's what genuinely stunned scientists, even the people who built the thing. In just over 10 hours of test observations, before the real survey had even officially begun, this telescope had already captured millions of galaxies and Milky Way stars, and had already spotted thousands of asteroids inside our own solar system. 10 hours. Most observatories take years to build a catalog of that scale. Rubin managed it in less than half a day of testing. After first look, the team moved straight into commissioning, fine-tuning the telescope and testing every part of the system to make sure the optics, the camera, and the data pipelines were all working exactly as intended before the real 10-year survey could officially start. During that testing window known as the early optimization surveys, something remarkable happened. In roughly 6 weeks, using nothing but this early test data, astronomers working with Rubin Observatory discovered more than 11,000 brand new asteroids that no one had ever recorded before. 11,000 in 6 weeks. That stands as one of the largest single batches of new asteroid discoveries ever submitted to the International Astronomical Union's Minor Planet Center, the official worldwide body responsible for verifying and cataloging small objects across the solar system. Inside that group, scientists identified 33 near-Earth objects, asteroids whose orbits bring them relatively close to our planet. None of these newly found objects pose any danger to Earth, but tracking near-Earth objects remains one of the most important jobs any observatory can do, because the more we know about them, the better prepared we are for whatever the future holds. On top of that, Rubin's early data also revealed 380 new trans-Neptunian objects, icy bodies, that orbit far beyond Neptune, out in the cold, distant edges of the solar system, where sunlight takes hours just to arrive. 2 of these newly discovered trans-Neptunian objects have extremely stretched, elongated orbits that carry them nearly 1,000 astronomical units away from the Sun at their farthest point. 1 astronomical unit equals the distance between Earth and the Sun, which means these 2 objects travel almost 1,000 times farther from the Sun than we do. That is deep, remote territory, and researchers believe studying orbits like these could eventually help confirm or rule out the long-debated theory of a hidden 9th planet, sometimes called Planet 9, potentially 5 to 10 times more massive than Earth, possibly warping the paths of distant outer solar system objects. Even if Rubin never spots such a planet directly, finding more objects with warped orbits would still stand as an important clue pointing toward its existence. That same early batch of data also allowed scientists to refine and correct the orbits of more than 80,000 asteroids already known, objects tracked before, but whose paths through space were not fully precise. With Rubin's frequent, detailed observations, astronomers sharpened those orbital calculations, making the entire map of the solar system more accurate than it has ever been. Then, in January of 2026, something else turned heads across the astronomy community. Using data gathered during this first look period, scientists published the very first peer-reviewed scientific paper based on observations from this camera. What they found was genuinely record-breaking. Hidden inside the data was the fastest spinning asteroid larger than 500 meters wide ever recorded, sitting quietly in the main asteroid belt. Researchers explained that an object like this simply could not have been detected without the unique speed and sensitivity built into Rubin's camera, and that finding thousands of new asteroids in such a short window and learning this much about them was only a small preview of what the full 10-year survey is going to uncover. Then came the moment that really opened the floodgates. On February 24th, 2026, Rubin Observatory issued 800,000 alerts to astronomers in a single night. 800,000 separate events flagged in one night alone. New asteroids appearing, stars suddenly exploding as supernovae, distant supermassive black holes flaring as they feed on surrounding material, and variable stars whose brightness rises and falls over time. Astronomers called this the true beginning of the alert stream, one of the final milestones standing between the observatory and the official start of its 10-year mission. And that mission did begin. On June 30th, 2026, the Legacy Survey of Space and Time officially started, following years of construction, testing, and a careful operational review of technical readiness, data quality, and calibration accuracy. From that night forward, Rubin Observatory began scanning the entire southern hemisphere sky over and over every 3 days, collecting close to 10 terabytes of data every single night, with some estimates placing that figure even higher once the survey reaches full operating speed. Across the full 10 years, the observatory is expected to generate roughly half an exabyte of information in total, an amount so enormous that entire teams of scientists and engineers have spent years building the algorithms needed just to sort through it. Scientists have said the amount of data Rubin gathers in its first year alone will be greater than everything collected by every other optical observatory on Earth combined. Not close to it, greater than all of them put together. Read that again, because it's the number that puts everything else in this story into proper scale. Once the survey reaches full capacity, the system is expected to send out as many as 7 million alerts every single night. 7 million. And each one represents a real change happening somewhere in the sky. An asteroid shifting position, a star exploding, a black hole flaring, a distant galaxy changing in brightness. Officials working on Rubin operations have pointed out that the millions of alerts generated in just the first couple of months alone already prove the observatory is up and running as a genuine discovery machine. Teams are using artificial intelligence and machine learning systems specifically built to sort through this flood of information in real time, because there is simply no way a group of human astronomers could manually review 7 million nightly alerts on their own. The automated filters sift through the noise and flag the events that matter most, so researchers around the world can react quickly, sometimes within minutes, and turn other telescopes toward whatever unusual event Rubin just detected. This is part of what scientists call multi-messenger astronomy, studying the universe using multiple types of signals at once, light, gravitational waves, and cosmic rays working together. When Rubin spots something like a possible collision between two extremely dense objects, or a sudden explosive event somewhere in the sky, it can immediately alert observatories around the globe to point their instruments at that exact spot, so the event can be studied from every possible angle before it fades away. Supernovae are one of the clearest examples of why this speed matters so much. A supernova occurs when a massive star reaches the end of its life and explodes in a burst of light powerful enough to briefly outshine an entire galaxy. These explosions do not last long. They brighten quickly and then fade over days or weeks, which means that if nobody is watching the right patch of sky at the right time, the event simply gets missed. Older telescopes, moving slowly and covering small patches of sky, missed enormous numbers of these events for exactly that reason, because nobody was looking in the right place at the right moment. Rubin Observatory solves that problem by essentially never looking away, because it revisits the same regions of the sky every 3 days. Every explosion, every sudden flare, every fading afterglow gets caught somewhere in that repeating cycle of images. The moment the system detects a sudden change in brightness matching the pattern of a supernova, it sends out an alert within minutes, giving astronomers around the world the chance to point other instruments at that exact location while the explosion is still unfolding. This is exactly the kind of multi-messenger, global teamwork scientists have been working toward for years. One observatory acting like a smoke detector for the entire southern sky, and dozens of other telescopes racing to respond the moment the alarm goes off. One of the deputy directors of Rubin operations at SLAC described this entire journey in a simple, honest way, explaining that it took 20 years of hard science, engineering, and determination just to reach the point where the team could finally start rolling on what he described as this blockbuster movie of the universe, and that the millions of alerts generated in just the first couple of months of testing already proved the observatory works exactly as intended. A genuine discovery machine, fully assembled and finally switched on. A planetary scientist at Caltech, who has watched this project develop since his early days in graduate school more than 2 decades ago, said that working with Rubin's data now feels like something he could only have dreamed about back then, watching a project take shape over 20 patient years and finally become real, working, functioning science. He also pointed out something worth remembering. If you ask 50 different astronomers what they are most excited to find using this telescope, you would likely get 50 completely different answers, because this one survey genuinely touches nearly every corner of modern astronomy and astrophysics at the exact same time, all at once, every single night. Over the coming 10 years, scientists expect this survey to reshape what we know about our own solar system in a fundamental way. Researchers predict Rubin could help triple the total number of known asteroids and increase the number of identified trans-Neptunian objects by nearly 10 times what is currently cataloged. Every single discovery adds another piece to the puzzle of how our solar system formed billions of years ago, how planets and smaller bodies settled into the orbits we see today, and what forces shape the outer edges of our cosmic neighborhood. But the larger goal, the reason this observatory carries Vera Rubin's name in the first place, reaches even further than asteroids and comets. Scientists are hoping this 10-year survey finally delivers real answers about dark matter and dark energy, the two biggest unsolved mysteries in modern physics. Dark matter appears to make up roughly a quarter of everything in the universe, yet it has never been directly seen, only detected through its gravitational fingerprints on galaxies, the very same fingerprints Vera Rubin first noticed decades ago. Dark energy is even stranger, the mysterious force that seems to be causing the expansion of the universe to accelerate rather than slow down the way gravity alone should cause it to behave. By watching billions of galaxies over 10 full years, tracking how they move, how their light shifts, and how the structure of the universe evolves over time, scientists hope Rubin Observatory can finally help explain what dark matter and dark energy actually are, something no telescope in history has ever fully managed to answer. It's worth pausing on why speed and repetition matter as much as raw resolution here, because that's the detail most casual coverage skips past. A single beautiful image of a nebula or a galaxy cluster is valuable on its own, but it's a snapshot frozen in time, one moment out of billions. What actually makes Rubin Observatory different from almost every telescope that came before it isn't just the size of its mirror or the megapixel count of its camera. It's the fact that it returns to the same patch of sky again and again, every 3 days, for 10 straight years, building not a photograph, but a timeline. That timeline is what allows scientists to catch a supernova within hours of it beginning, rather than days after it has already faded. It's what allows an asteroid to be flagged, not because someone happened to be looking at exactly the right coordinates on exactly the right night, but because the system is, in a very real sense, always looking. Astronomy has spent centuries working around the limitation of only being able to watch a small slice of sky at any given time. Rubin Observatory is the first serious attempt to remove that limitation almost entirely across an entire hemisphere. That shift has direct consequences for planetary defense, and it's a piece of the story that deserves more attention than it usually gets. Every near-Earth object cataloged by this survey adds to a global effort to understand which asteroids might someday pose a genuine risk to our planet. None of the objects found so far are considered dangerous, but the value of a survey like this isn't limited to what it finds in its first year. It's about building a complete enough map of the solar system that nothing capable of reaching Earth can realistically stay hidden for long. Older survey programs worked through this problem slowly, one telescope covering one region of sky on an inconsistent schedule, gradually building a partial picture over decades. Rubin compresses that timeline dramatically, and researchers involved with near-Earth object tracking have described this as one of the most meaningful practical benefits of the entire project, separate from anything to do with dark matter, dark energy, or distant galaxies. The trans-Neptunian discoveries carry their own kind of significance that goes beyond simply adding numbers to a catalog. Every icy body found drifting at the far edge of the solar system is a fragment of the same disk of material that the planets themselves formed out of billions of years ago. Studying how those objects are distributed, how their orbits are shaped, and where clusters of similar objects appear, gives scientists a way to reconstruct events that happened before Earth existed in anything like its current form. The two extreme, elongated orbits found during Rubin's early testing phase are a perfect example of why this matters. An orbit that stretches nearly 1,000 astronomical units from the Sun doesn't happen by accident. Something had to shape it, whether that's a close encounter with another star billions of years ago, gravitational interference from an undiscovered planet, or forces still not fully understood. Each new object with a similarly warped path adds another data point to a puzzle that has been debated by planetary scientists for more than a decade. The scale of the data pipeline behind all of this deserves its own explanation because it's easy to focus purely on the images and forget just how much infrastructure has to function correctly every single night for those images to mean anything. Every exposure captured on the mountain in Chile has to be transferred, calibrated, cross-referenced against previous observations of the same patch of sky, and checked for anything that changed since the last visit, all within minutes, so that alerts can go out while an event is still unfolding. That requires a level of automated processing that didn't meaningfully exist for astronomical surveys even a decade ago. The artificial intelligence systems built for this project aren't simply sorting through noise for convenience. They're performing a task that would be functionally impossible for any team of human astronomers working manually, comparing millions of new data points against an enormous historical archive every night without exception, and flagging the handful that represents something genuinely new or unusual happening in real time. There's also a deeper story here about how dark matter and dark energy research actually works, because it isn't the kind of science that produces one dramatic breakthrough moment the way a single photograph or a single asteroid discovery might. It's built entirely on statistics, on measuring the shapes and positions of enormous numbers of galaxies with extreme precision and watching for tiny, consistent patterns of distortion caused by invisible mass-bending light as it travels toward us. That technique, known broadly as gravitational lensing, only becomes powerful when applied across billions of galaxies rather than thousands, because the individual signal from any single galaxy is far too small and noisy to mean anything on its own. This is precisely why a 10-year survey covering an estimated 20 billion galaxies matters so much more than any single deep field image ever could. Dark energy research works in a similar way, relying on tracking how the large-scale structure of the universe, the way galaxies cluster and spread apart over cosmic distances, has changed over time. Only a survey with Rubin's combination of depth, area, and repeated observation over a full decade can gather data at the scale these two questions genuinely require. Think about everything this single machine is doing at once. It is mapping our own solar system in more detail than ever recorded. It is discovering tens of thousands of new asteroids, some of which may one day matter for planetary defense. It is catching supernovae the moment they explode, giving scientists a front row seat to some of the most violent events in the universe. It is tracking supermassive black holes as they flicker and flare across billions of light years of space. It is building toward a full catalog of an estimated 20 billion new galaxies. And underneath all of that, it is quietly gathering the exact kind of data that could finally crack open two of the biggest mysteries human science has ever attempted to solve. And this is still only the earliest stretch of a 10-year mission. Everything described here, the 11,000 asteroids, the record-breaking spinning space rock, the 800,000 alerts in a single night, the trillions of pixels inside a single image, all of it happened before the official survey had even fully begun. The real 10-year clock only started ticking on June 30th, 2026. Every single night from here forward, this telescope keeps watching, keeps scanning, keeps capturing data at a scale no observatory on this planet has ever managed before. And somewhere in that flood of nightly images, hiding among millions of galaxies and thousands of newly discovered asteroids, there is a very real chance that Rubin Observatory ends up capturing something genuinely unexpected, something nobody has predicted, simply because it is watching the sky more closely, more often, and in more detail than any instrument in the history of astronomy. That is the part of this story worth sitting with the longest. Not any single asteroid count or alert total, impressive as those numbers are, but the fact that for the first time, humanity has built a machine that essentially never stops watching. Every 3 days, the same patch of sky gets revisited. Every 40 seconds, a new exposure gets taken. Every single night, roughly 1,000 images get added to a data set already measured in the trillions of pixels. Most of what this observatory finds over the coming decade has not been predicted by anyone, because it can't be. That is the nature of a genuine survey instrument. It doesn't go looking for one specific answer the way a targeted mission does. It simply records everything continuously and lets the discoveries surface on their own schedule, whether that means a hidden planet at the edge of the solar system, a supernova caught within minutes of igniting, or a fingerprint of dark matter hiding somewhere inside the motion of 20 billion galaxies. Remember, this observatory is only a few weeks into a mission built to run for 10 full years. Every single one of those years is going to bring fresh batches of asteroid discoveries, fresh supernova alerts, fresh images of galaxies nobody has ever cataloged before, and slowly, piece by piece, real progress toward finally understanding dark matter and dark energy, the two mysteries that gave this telescope its name in the first place. There's a broader shift happening here too, one that goes beyond any single discovery this observatory produces. For most of the history of astronomy, access to serious data required access to serious infrastructure, a research position at a major university, time allocated on a limited number of large telescopes, and years of specialized training just to interpret what came back. Rubin Observatory is built around a fundamentally different model, one where an enormous, continuously updated stream of professional-grade astronomical data becomes available to researchers far beyond the small circle of institutions that could previously afford this kind of access. That doesn't just mean more papers get published. It means problems that used to take decades to chip away at, cataloging the solar system, tracking transient events across the sky, measuring the large-scale structure of the universe, can now be worked on simultaneously by teams scattered across dozens of countries, all pulling from the same continuously growing archive. It's a genuinely different way of doing astronomy, built for an era where the bottleneck isn't how much sky you can photograph, but how much of what you've already photographed you can actually make sense of. That shift alone, quietly happening in the background of every headline about asteroids and nebulae, may end up being one of the most lasting contributions this observatory makes to the field, long after any individual discovery from its opening months has been folded into the routine, expected output of a survey running exactly as designed. Somewhere on that mountain in Chile, right now, the shutter is opening again, another 40-second exposure beginning, another small piece of the largest cosmic movie ever attempted quietly being recorded, with 9.5 years still left to run.